Hello everyone, my name is Reyhaneh Jabbarvand from University of Illinois, and this work has been done in collaboration with Forough, Mehralian and Malek from UC Irvine. Let me start by reminding that our world is going mobile and on the cloud, which makes energy efficiency a first-class concern in these emerging computing domains. Specifically on battery-constrained mobile devices, presence of energy defects can negatively impact user experience. But what are energy defects? By a high-level definition, energy defects happen when execution of a code causes unnecessary energy consumption. And the root cause of such issues is typically misuse of hardware elements on the phone at the software level by applications. To make it more clear what are energy defects, I will show you specific examples of them in the next slides. So, suppose that you have a tracking application, something similar to the Google Map. This snippet here shows a high-level code of tracking user location. When user starts her activity, this code registers a location listener that uses GPS as a source of location information. It is developers' responsibility to adjust the frequency of listening to location updates based on the speed of user, and developer can do so by controlling the time and distance parameters in the request location update API. But if developer fails to do so, and even worse, if populate the time and distance parameters with some small values, the application will listen to location updates as frequent as possible. This means that the energy-hungry GPS hardware will be unnecessarily utilized at a very high rate, and battery drains faster than it is expected. One of the best ways to assess the energy efficiency of applications is through testing, and several automated test generation techniques have been proposed in recent years to advance the energy testing. However, none of them address the Oracle problem in a comprehensive and scalable fashion, and in fact, generally speaking, automated test Oracle construction is extremely hard problem. So, there is a demand for automated energy test Oracle construction. Our intuition to solve the Oracle problem was that since energy defects manifest themselves under peculiar conditions, then a feasible solution to detect them could be to monitor for certain changes in the state of software and hardware elements during the test execution. To give you an example, the unnecessary location update energy defect that I showed earlier in the presentation can be detected during the test execution if we can observe this pattern in two consecutive states of user movement and GPS hardware. This pattern indicates that while the user is stationary and her movement does not change in two consecutive states, the GPS is on and there is an active location listener that unnecessarily engages the GPS hardware. Based on this intuition, we hypothesized that by using a deep learning technique that can learn the misbehaviors corresponding to the different types of energy defects during the test execution, we can construct an automated oracle to effectively predict the test execution output. Generally speaking, a deep learning technique should include three main components. First of all, we need to identify a set of features that can represent the characteristics of the phenomena that need to be observed. Next, we need to identify which deep learning model is suitable for the problem. And finally, we need a dataset representative of the problem domain so that the deep learning model can learn the patterns from the dataset. In the remaining of this talk, I will explain each of these components for our proposed Oracle construction technique, which is called ACETON. The feature vector in ACETON should be able to distinguish the characteristics of different types of energy defects. To that end, we chose them to reflect the properties related to the state of software and major energy-greedy hardware elements. More specifically, the feature vector, which I collectively refer to it as state vector or SV for short, consists of 84 binary features that represent different aspects of app's lifecycle and hardware elements that needs to be monitored during the test execution. For example, the SV contains 6 entries for the Bluetooth hardware, and these entries capture different states of Bluetooth that can be taken under different settings. After the feature engineering, it is time to select proper model for the Oracle construction. This learning module should get a sequence of SVs which are sampled at a fixed rate during the test execution as an input and predicts whether a test passes or fails as an output. A suitable learning model for this problem needs to satisfy some criteria. First of all, it should be a supervised learning model, as the Oracle construction is a classification problem. Also, the data here is sequential and relatively high dimensional, where each data point consists of approximately 2100 values, so the model should be able to deal with such data. Finally, energy defects could happen anywhere during the test execution, and the learning model should be able to detect at which SV indices the energy defect happened. Given these criteria, ACETON leverages long short-term memory or LSTM neural networks augmented by the attention mechanism in order to construct an oracle for energy testing. In the next slides, I will provide an overview of ACETON's architecture. LSTM consists of a chain of repeating modules of neural network which makes it capable of learning long-term dependencies, so it can remember the patterns in the inputs that will persist. Attention mechanism is a method for making LSTMs handle long sequences by reminding the network where it has previously looked as it performs its task. The attention layer in ACETON serves for two purposes. First, it improves the performance of learning. Second, it enables interpretability and can verify the validity of learning to ensure the high performance of the model is not fake due to the problems such as data leak. In the next slide, I will elaborate how ACETON interprets the outputs through additional attention analysis. ACETON leverages attention weight vector, which is a product of attention layer, in order to perform additional analysis to determine which features were involved in the decision of label for a given input. I refer to these features as attended features. Our biggest challenge in attention analysis was that the attention of the model to sampled SVs varied depending on where the energy defects happen and how long they last. But through experiment, we realized that regardless of this variation, the model predicts label by attending to the SVs whose indices were between the biggest jump and biggest drop in the attention weight vector. Based on this observation, we designed an algorithm for attention analysis, and at a very high level, it works as follows. For a given SV sequence and attention weight vector, It finds the features that are common in SVs, whose indices are between the biggest jump and biggest drop in the attention weight vector. These common features may contain irrelevant features that do not change during the entire test executions. For example, the display on feature, because the display is on during most of the test execution. Attention analysis identifies such features by comparing the features that are common between the attended SVs and their exact predecessor, and then excludes them from the common features. So the resulting set of features would be the attended features. Finally, if the category of the attended features corresponds to the predicted labels, it means that the model has considered relevant features in order to predict the output of the test execution. Now that we have identified proper features and selected an appropriate model, it is time to train ACETON with large amount of high-quality training data. For the purpose of data generation, we use MuDroid, which is an energy-aware mutation testing framework. This framework has 295 mutants that are representative of diverse types of energy defects, accompanied by 329 high-quality developer-written tests. Also, it categorizes the mutants based on the hardware elements that they misuse, which enabled us to generate a fine-grained labels using this dataset. Specifically, instead of just having the pass and fail labels, ACETON is able to generate 7 labels where the fail labels represent the type of failure and can be further helpful for the debugging purpose. This is an overview of the MuDroid dataset, which provided ACETON with approximately 2 million training instances. More specifically, MuDroid provided us with 16K pairs of mutant tests, and execution of each test on a mutant provides 120 SVs that gives the model about 2 million of sequential instances to be trained on. After construction of the dataset and implementation of the ACETON, which are all publicly available, we evaluated from different aspects that you can see here. For a proper evaluation of the effectiveness, we performed 3 separate set of experiments. In the first experiment, we repeatedly and randomly split the dataset and used a subset for training the oracle and another subset for testing. In the second one, we trained the model on the whole dataset and used real energy defects for testing. And in the third experiment, we removed a subset of defects, trained the model on the remaining dataset, and used the unseen defects for testing. And here are the results for the first experiment. Each row in this table shows the number of test instances in the actual class, and each column indicates test instances in the predicted class. As you can see, except 3 passing tests that were misclassified as failed location, ACETON was able to predict all other labels correctly. So, ACETON is able to detect the outcome of tests in mutants with a very high precision and recall. But what about the real energy defects? To evaluate that, we used a dataset with 14 real-world Android apps with real energy defects confirmed by their developers, which had corresponding tests to reveal energy defects. The dataset also included information about the misused hardware elements that we used as a ground truth for the labels. Highlighted columns in this table demonstrate information about the dataset. And as a result of this experiment show, ACETON was able to correctly identify the outcome of tests on all the subjects. Previous experiments evaluated effectiveness of ACETON in detection of defect types that it was trained on. However, we also wanted to investigate its ability to detect previously unseen energy defects. Well, of course, machine learning does not have some superpowers to know everything in the universe, and it should see and learn the patterns in order to predict them. However, we hypothesized that if ACETON is trained on a subset of defect types for a specific hardware element, it might be able to detect unseen defect types related to that hardware as well. For this experiment, we excluded a subcategory at a time from the dataset, for example, N1 in this table, and used it for testing. Then we trained the model on the energy defects related to all other subcategories. For this experiment, we only measured the recall parameter, as the data only belongs to one subcategory for the test, and no false positive will be generated. As you can see here, our results show that in majority of cases, ACETON is able to effectively detect previously unseen energy defect types with an average of 93% recall. At the next step, we evaluated usage of attention mechanism in ACETON. As a reminder, the results of first research question showed that ACETON is able to predict the labels with a high precision and recall. To see the impact of attention mechanism on these results, we removed the attention layer from ACETON and repeated the experiment. Here are the results. As you can see, compared to the initial results, more misclassification happens without the attention mechanism. And this negatively impacts the performance of the model and in some cases even causes a drop between 12 to 34% in the precision and recall values. Our novel attention analysis also enables interpretability and can serve as a verification to its validity. To evaluate validation of the learned model, we wanted to see if the model predicts labels by attending to the relevant features. To visually confirm that, we created a heat map that you can see here, where the horizontal axis indicates the features in the state vector and vertical axis shows defect types. In this heat map, the more a feature in SV has attended in the decision, its color is closer to yellow. As you can see, the attended feature corresponds to the categories of defects in all subcategories, which confirms the model indeed attended to the relevant features in order to predict the output of the test execution. We also wanted to see if ACETON is reusable across different devices. To evaluate that, we used two devices which were not only different in terms of the Android versions running on them, but also had different hardware configurations such as pixel density and CPU frequency. Then we trained the oracle on both devices separately in order to see if the oracle trained on one device can correctly predict the label of tests executed on the other device. The results of this experiment showed a high precision and recall for the oracle trained on a different device, which confirms our energy oracle is device independent and reusable. Finally, we evaluated the performance characteristics of ACETON. On average, it takes 4.5 minutes for ACETON to train the oracle on the whole dataset, and after training, it takes approximately 37 milliseconds on average to predict the label for a test data. These results confirm that our proposed oracle is fast and scalable. In conclusion, we saw a scalable and comprehensive solution for automated oracle construction in the domain of energy testing. The proposed approach leverages deep learning to learn the misbehaviors corresponding to different types of energy defects during test execution, and it is able to predict whether a test can reveal an energy defect or not promptly and with a high precision and recall. More importantly, the approach is interpretable, and we were able to show that the model indeed attended to relevant features in order to decide the test execution output. While the proposed idea solves the oracle problem for energy testing, we believe that it opens an avenue to address the test oracle automation challenge in general. Thank you very much for your time.